Alright, so for this video lesson we're going to talk a little bit about the interactions between magnetic fields and conductors, or magnets and conductors, either way you want to look at it. This interaction is really important for some of the semiconductor applications. It's also important for motors. Motors need the wires moving in magnets. And so we'll start off with a real simple example. It's the magnetic field around a current-carrying wire. And so if you just have a long, thin wire with a current running through it, there will be a magnetic field around it. And that goes back to how Ørsted found out there was this interaction between magnetism and electricity. And to figure out what direction things are moving in, we end up using a second right-hand rule, where your thumb goes in the direction of the current in the wire, and the curl of your fingers gives you the direction of the magnetic field. So in the picture that's on the screen right now, the thumb is pointing upwards with the current, and the field is coming out of the paper on the left-hand side and going back in on the right-hand side. And you can see that in the circular motion. And of course, where there's a magnetic field and a current, we're going to have some kind of a force on a wire. And for that example, we're going to place a current-carrying wire into a uniform magnetic field. So now we're going to take a wire with a current in it, and we're going to stick it into a magnetic field. And it's a uniform magnetic field, and the one that I have drawn, the field is coming out of the paper towards us. And so if you use the right-hand rule, you can figure out which direction the force is going. So your thumb is in the I, current direction, and your finger coming out of the middle finger coming out of the board here. And so the force is going to be upward. So the magnetic force is going to push the wire upward in this field. And then we need to come up with a way to calculate this. And so we start with just the equation for force in a magnetic field, and we have F is QV cross B. And if you think about a wire, the amount of charge is going to be some number times a charge, just the charge on an electron, times the volume, which is cross-sectional area, times length. So that's where that Q is equal to NEAL comes from. That's going to give you the total charge in your wire, however long it is and however big around it is. And then the other piece is that that velocity vector is the direction that the charge is moving. So it's going to be the drift velocity. And you can find that by the magnitude of the drift velocity and then some little vector in the L direction. And so we can rewrite this equation as NEA drift velocity, and then do a cross product between the length of the wire and the field. And then if you remember back to the equation of drift velocity, the current is equal to NE area times the drift velocity. So that's a rearrange of that equation. And so what we end up with is, so it's the current times the length vector crossed with the magnetic field vector. All right, so for this example, we have a wire, long wire, carrying 5 amps of current, placed in a uniform magnetic field of 0.3 Teslas. So it's shown below. So the wire is in the Y direction, current's moving in plus Y, and also our L vector is going to be in the plus Y direction. And then our magnetic field is in the plus X direction. And when you do the cross product between the Y and the X, you're going to get a negative Z. So just keep that in mind. So the L cross B is going to give us something with a negative K hat. So our force equation, force is current times L cross B, and then that's a 90-degree angle, so it's just I LB. And remember, we have to still have to keep in mind our direction, and so we get the current 5 amps times 0.3 Teslas. And in this case, we don't know our length, so we're going to end up with a force per unit length, and it's 1.5 newtons per meter K hat, and remember it's negative K hat. All right, so what if B is not perpendicular to the wire, but it's off at a 30-degree angle from the X? And so if you have to go through and solve for the components, so it's going to be breaking into the components for I hat and J hat, and then plug that into the equation. So you can still plug in B with its components. And since I didn't identify an L in this, we're just going to leave L as L. And we're once again going to go through and find the force per unit area. So force over L is going to be, this first one is 1.5 Teslas cosine. And then when you do J cross I, you end up with K hat. And then the next one just ends up being 0 because J cross J is 0. So the force per unit length is going to be, oh, forgot the minus out there, sorry guys, minus K hat, minus 0.13 K hat. And it does make sense that the force is smaller in this instance because the maximum force is going to be where the field and the velocity or the current are perpendicular. And so the next topic is going to be where you have forces and you have currents and you have loops of wire, which is how motors are going to work. You're going to end up with torque on that rotating wire. You're going to rotate the wire in the field and end up with a torque on it. And what's interesting about this situation is when you have a loop of wire that's carrying a current, the net force on the wire is 0 due to the symmetry, because you've got each one of the forces from the field pointing in opposite directions, plus X minus X, plus Z minus Z, according to the drawing that we have there. But what you do have is a torque on the wire due to the rotation. So you're going to end up with 2 of those forces contributing to some sort of a torque. And the equation that you see in front of you, current times area times the magnetic field times the sine of theta, defines that torque. And so it's current, area of the loop, B is the magnetic field that it's in, and the sine of theta is the angle. At theta there is the angle between the normal to the plane of the loop and the magnetic field. All right, so here's our example where we're going to find the torque on a loop of wire. So it's a square loop, 18 centimeters on each side. Remember to change those to meters. And it's a bunch of wire looped around and around and around. That makes 150 turns. So around, around, around. We're going to put it in a 1.6 Tesla magnetic field, and it's going to be at an angle of 11 degrees to the field. And so first we start by finding the torque on one loop, and that's just the current times the area times the field times the sine of the angle in between it. So it's going to be 50 amps, and in this case 0.18 meters squared, because it is a square, 1.6 Tesla sine of 11 degrees. And if you work all that out, you get 0.49 Newton meters, and that's for one loop. And so if we have 150, then the torque is 150 times the torque for one loop, and we end up with 74 Newton meters. And there's another way to find the torque on the field, and it's by using the magnetic dipole. Since magnets come in dipoles, you start off with that IAB sine theta, and the equation for the magnetic dipole is the current times the area, and it is a vector, so it's going to have that n hat vector, the perpendicular to the plane, and to find all the directions, you would use your thumb in the direction of n hat, and then your fingers curl around the current, and it'll tell you which way n hat goes, either to which way out of the plane, forward, backward, up, down. When you do the substitution for the torque in terms of the magnetic dipole, you get the mu cross B because of that sine theta. So one last piece to this is the Hall effect, and this comes into play with a lot of small metals. When you're talking about currents and conductors, we like to talk about things that are, very, very long, very, very wide, infinite planes. Well, in this case, when you're talking about smaller things, you have to talk about edge effects. And so the Hall effect is actually due to the current flowing and the magnetic field. And what happens is that magnetic field deflects those charges in the current, and it pushes the positive charges to one side of the conductor and the negative charges to the other side of the conductor, and you end up kind of building up almost a parallel plate type thing inside this piece of metal or this conductor. And that the potential difference between either edge is called the Hall potential. And from at some point, the motion of the charges is going to get to an equilibrium state, and with the forces, and you can say that the forces are equal, electric and magnetic force, and so the drift velocity, which is the current, is going to be the electric field divided by the magnetic field. And if you work your way through all this, you end up with a equation for the Hall potential. So it's either one is handy for you, depending on what information you have in your problem. You can have the field times the current times the drift velocity, or if you need it in more detail, where you get areas and densities and things, there it is, current times magnetic field times the distance between the edges where the charge is spread to, and the N times E is going to be the charge density times the charge, and then A is the cross-sectional area of your piece of metal. All right, so here is our Hall effect example. We've got a piece of silver, has a charge density of 6 times 10 to the 26 electrons per meter cubed, so it's a volume density. It's 1 centimeter wide, and it is 0.2 of a centimeter thick. And because it's so little, we have to think a little bit about edge effects, and that's where the Hall effect comes in. It has a current of 100 amps passing through it, and we're going to put it in a magnetic field of 1.5 Teslas, and we're going to want to find the Hall potential across the metal. And so we just use the Hall equation. So it's nice and straightforward. Once again, you have to watch out for your units. So since this is 1 centimeter, it is 0.01 meters. And we have 6 times 10 to the 26 And that number comes from just a property of silver, so that would be given to you. Charge on an electron, and then the area, so it is that the thickness, that's the cross-sectional area, so it's the thickness times the distance across. And so our Hall voltage ends up being 7.8 times 10 to the minus 6 volts. So it's tiny, tiny, tiny effect, but it is there.